Large language models often mirror the internal neural geometry of a human brain during creative tasks. However, research into post-training methods suggests that optimizing models for step-by-step logic can push their internal representations away from that human-like baseline. Researchers analyzed this connection using fMRI data from 170 subjects performing the alternate uses task, a psychological test designed to measure divergent, out-of-the-box thinking. This diagram outlines the experimental pipeline. By comparing fMRI recordings against the hidden processing layers of various language models, the study used representational similarity analysis to quantify the structural match between human and artificial cognition. This method allows us to map an artificial model's internal architecture directly against the physical networks of the human brain to see how closely their processing styles overlap. This scatterplot tracks model size against neural predictability. The data shows that larger models, scaling up to 70 billion parameters, naturally exhibit higher alignment with the human brain's default mode network during the initial stages of a creative task. This similarity is not uniform across the entire model. The strongest correlation with human brain activity occurs within the deepest, most computationally complex layers of the AI. This timeline visualizes a stage-dependent limitation. While models match human neural patterns closely during the prompt stage, this alignment weakens the moment the model begins generating its text response. This suggests that while artificial systems can mirror the human ideation process, the autoregressive method of outputting language token by token represents a divergence from human biological cognition. Fine-tuning a model for specific tasks reconfigures its underlying alignment, often creating a trade-off between logical processing and human-like neural similarity. This bar chart shows the impact of training objectives. A reasoning-trained model showed negative alignment with high creativity human responses, moving away from human ideation. In contrast, the creativity-optimized model's upward-pointing bar successfully maintained neural similarity to creative human responses. These results indicate that training models to follow strict logical chains of thought can steer their internal representations away from the neural geometry associated with human creative ideation. Currently, AI development focuses heavily on convergent thinking, tasks like math and coding, where the goal is to arrive at a single verifiable answer. If post-training continues to favor these convergent tasks exclusively, we risk degrading the model's capacity for the divergent thinking required for innovation. Integrating brain alignment metrics as a standard benchmark could help ensure future models maintain a balance between logical accuracy and creative potential. To build systems capable of solving complex, open-ended problems, we must protect the structural processing styles that allow for human-like innovation.